In this video, we're going to introduce sequences and talk about limits of sequences. This is going to be the first of 3 videos that we have on the topic of sections 10.1 and 10.2 of the book. I'm making a slight deviation from what the book does in that I'm treating them together as one lump because I feel like that's more natural. So with that said, let's jump on in and define what a sequence is. So the key thing to keep in mind is that a sequence is a list of numbers. And more importantly, a sequence is an infinite list of numbers. So here's an example. We have a list that goes 1, 1/2, 1/3, 1/4. And so the nice thing about this one is that there is a clear pattern. So that means that we are not dishonest in writing that list down. And what we mean is the next term. So let's do a couple more terms. We get 1/5, 1/6, 1/7, and so on and so forth. And obviously we're not going to write down all of them. Okay, that's one way of describing an infinite list of numbers. It's a little bit awkward in that not every list is that clearly specifiable, right? There are going to be many lists that are going to be awkward to work with and where it's just really uncomfortable to write down a list of terms so that we can try to guess what the terms are. So we have 3 basic ways of representing lists of numbers. We can represent it just as a list as we just did. So here we've changed the list slightly. Now we have powers of 2. We get 1, 1/2, 1/4, and 1/8. And so then the next terms are going to be a 16th, a 32nd, a 64th, and so on and so forth. Okay, I have a punctuation problem here, but otherwise we can see it as a formula. Right? We can work with a formula where we think of our terms in the sequence as being described by a formula. And given the formula I wrote down, I'm thinking of this term as a 0, that next term as a 1, that next term as a 2, and so on and so forth. And I'm saying if you want to find, let's say, the A3, right, we're going to use our formula. We get 1 over 2 to the 3, and that's going to give us 1 over 8, which indeed matches the A3 that we saw in our list already. Right, so that's another way of describing these numbers. We can describe them by a formula. And then finally, we can describe them by a relationship from one term to the next term in the list. Right, so we can say that to go from that guy to that guy, we multiply by 1/2. From that guy to that guy, we multiply by 1/2. And from that guy to that guy, we multiply by 1/2. Right, so we're describing each term in the sequence by its relationship to the predecessor. So that's what we call a recurrence relation, where we describe each one by its relationship to the predecessor. But in order for that to make sense, we need a starting point. Right, so here we have to specify the first term, this A0, and then all the subsequent terms are given by their relationship to their predecessor. Okay, there are many classic sequences that we can define. So let's take a look at one that is a very traditional sequence defined by recurrence. And this is something called the Fibonacci sequence. So here, the Fibonacci sequence, each term in the list depends on its 2 preceding terms. So this is a recurrence relation where we have that the first 2 terms are, well, we start at n equals 1 in this example. We have 1, 1, and then, right, so that's F1, F2, and then F3 is going to be, right, that's n plus 2, that means n equals 1 here. So we have F1 plus F2, so that's going to be 1 plus 1, so that guy is equal to 2. And then F4 is going to be, from our formula, that's going to be f2 plus f3. So that means that we get 2 plus 1. I'm sorry, I'm saying that backwards. We have, so f2 is 1, and f3 is 2. So that's 1 plus 2 gives me 3. And then f5 is going to be the sum of the two predecessors. So that's going to be 2 plus 3 is 5. And then the next term is going to be 3 plus 5, which is going to give me 8. And then we keep going like that. So the next term after that would be 8 plus 5, which gives us 13. And we keep going along this pattern. Okay, so then this is an example of a quite complicated recurrence relation. And there is a formula. There is a formula for the Fibonacci numbers, but it's not at all an obvious formula. And so the formula for Fn is not obvious. Now, because these are lists of numbers, we don't really care if we write a formula that starts at a different n value. So we're allowed to play a game called re-indexing. So we will think about sequences as being the same if you re-index them. So for instance, in our powers of 2 example, we have this 1, 1/2, 1/4, 1/8, etc. Well, we called that one A0, and that one's A1, A2, A3, but maybe we don't like that. Maybe we would like this guy to be the first term in the sequence with our index of 1, and this guy the second, and third, and fourth. Well, to fix that, all we have to do is just do what's called re-indexing. It's like a change of variables in the index. Okay, and then there's nothing magical about the letter n. We can use whatever letter we like. For instance, we could write bk is 1 over 2 to the k minus 1, or we could write bi is 1 over 2 to the I minus 1. For whatever reason, we traditionally work with K, N, M, L, these letters that are sort of in the middle of the alphabet there. It's one of these historical things, and it's not clear to me why it's like that. I think that'd be an interesting history of mathematics question. Okay. How do we visualize sequences? Right? Sequences can be a little bit hard to imagine. And I would say that there are two key ways of visualizing a sequence. The first way is to think of it by graphing it. Right? So if I have an is 1 over n, I can think of drawing myself an axis. I can imagine then graphing y equals 1 over x. Right, that's the graph y equals 1 over x. Okay, it's not a very good graph, but that's what it's supposed to be. And then we take a look at where the integers are. And then we get the corresponding dots here for my sequence. Right, so the first value of my sequence is given by that first dot. The second in the sequence is the second dot. Third in the sequence is the third dot. Fourth in the sequence is this dot. Fifth, etc. Okay, that's one method. The other method is for me to make a little number line and just decorate it with the terms in the sequence. And so let's make it nice and big. So that's 0 and 1. This is my number line. And so the A1 is here. Right? A1 is 1. A2 is there. And then let's cut this into thirds. A third is about here. Right, that's a third. That's a half. And then a quarter. And this is going to get a little bit crowded. And then so on and so forth. Right, we can keep drawing them on our number line. And that's another way of representing sequences and visualizing them. Okay, so the next thing we want to look at are limits of sequences. So sequences have limits, as we're going to be interested in a limit as n goes to infinity. And that we're going to treat exactly the same as we did when we were looking at limits of functions as we take x going to infinity. So it's going to be exactly the same thing, just a different variable then. So here, for instance, we're looking at the limit as n goes to infinity of n plus 1 over 2n squared minus n plus 5. And for that, we're going to play this trick that you learned in Cal 1, where we're going to write this and we're going to force factor out the highest power of n that shows up in this expression. So the highest power is n squared, so we're going to factor it out on the top and on the bottom. And the reason we're doing this is that this is an infinity over infinity form, so we can't conclude directly. And so here we get 1 over n plus 1 over n squared. And in the denominator, we're going to get 2 minus 1 over n plus 5 over n squared. Our n squareds cancel, so we're left with 1 over n plus 1 over n squared, whole thing divided by 2 minus 1 over n plus 5 over n squared. The numerator is going to 0 as n goes to infinity. The denominator is going to 2 as n goes to infinity. So that's a 0 over 2 form, and that's perfectly valid, right? That tells us this goes to 0. And that's as n goes to infinity. Okay, that looks an awful lot like an 8. Let me fix that. Okay, so that's a really simple example of looking at what a sequence does as n goes to infinity. Now, there are going to be slightly more complicated examples that we can look at, but we're going to see things that look exactly like we know from studying functions. And we have a very useful theorem, this so-called squeeze theorem. And so the idea is we suppose that we have 3 sequences. Okay, so we have these 3 sequences, and they are sandwiched. They squeeze the one in the middle. There's an is less than or equal to bn is less than or equal to cn. And if the 2 outside ones have a limit, let's say L, then the sequence bn also has a limit that's equal to L. Okay, and here I've introduced a little notation that people sometimes use for sequences, where you write bn with parentheses and then you say where the n starts and where it goes to. So here we have an example, which is find the limit of 3 plus minus 1 to the nth power over n squared. So this one, the key feature is that this minus 1 to the n, and this is something we're going to have to recognize. Minus 1 to the n is an expression that's going to be equal to 1 if n is even, and it's equal to minus 1 if n is odd. So this means that an, as I've given it to us, is sandwiched between 3 plus 1 over n squared and 3 minus 1 over n squared. Now the left term goes to 3, the right term goes to 3, so an is also forced to go to 3 by the squeeze theorem. And that's an example of this squeeze theorem. Let's use the squeeze theorem again to find another example. Right? So here this thing looks terrible, this cosine n squared minus 3. But the nice thing is that we know that cosine of anything is between minus 1 and 1. Oops. I started to put my fraction in the wrong place. Right, that guy is between minus 1 and 1. So that means that an is sandwiched between 1 over n and minus 1 over n. Now the guy on the left goes to 0, the guy on the right goes to 0, so an goes to 0 as n goes to infinity by the squeeze theorem. So that's another nice example of using the squeeze theorem. And again, this is something that we could have understood if we were thinking about functions. So in this regard, the sequences are exactly the same. In our next video, we'll see an example where sequences do something a little bit more interesting.